Hello again. Today we'll talk about a very important property, very important concept in control systems, that of BIBO stability, or bounded input, bounded output stability. Let me give you the following definition, the following concept. If we have a dynamical system, we will say that it is BIBO stable if the output of the system remains reasonable, doesn't go crazy, so long as the input is reasonable as well. What we mean by reasonable? We mean that the signal is bounded. So once again, a system, a dynamical system, with an input u and an output x, will be said to be BIBO stable if the output x is bounded whenever the input u is bounded. So u is bounded implies that x is bounded. And here is the definition written in this slide. What does it mean for a signal to be bounded? The definition is very simple. Let me perhaps better sketch it like that. The signal x is said to be bounded if somehow we can sketch it within this band over here. So if you can sketch your signal between a band from -m to +m, if it is a signal like that, whatever, then it is a bounded signal. It becomes clear that all constant signals are bounded. It also becomes clear that signals like x of t is equal to sine of t, or for example y of t is cosine of t, again are bounded. Why? Because sine has an absolute value of no more than 1. It can be sketched between -1 and 1. The signal z of t is 1000 times sine of t, might be, in a way, so to speak, in some context it might be a large signal, but again it's bounded. It is between -1000 and 1000. On the other hand, signals like x of t is equal to t, such a signal is not bounded. It's called unbounded because we cannot sketch it between -m and m for whatever m. It will always escape such a band. So a proper mathematical definition would be that a signal x is bounded if there is a number m, so that for all non-negative times the signal remains in that band that we talked about previously. Now I want to give you an example to demonstrate the concept of BIBO stability. An example from physics. Take this spring mass damper system, and we apply a force here, so the force is the input. And what we're looking at here, the output variable, can be the displacement x from the rest position. It is intuitively clear, we must prove it of course in control theory, but it becomes a little intuitively clear that if f is bounded, if it doesn't exceed, for example, 1 Newton, then the displacement cannot go unbounded. It cannot start running if you here just apply a finite force. There will be the restoring force that at some point will counterbalance the applied force F. So this is a BIBO stable system. Let's have a look at a counterexample, a non-stable system, an unstable system. Take here an inclined plane, actually think of it as an infinite inclined plane, and apply a force F is equal to 0, which is bounded. And let's say that the displacement x is the displacement from that original position on the plane. Then without friction, this will start sliding, and it will slide and never stop. So this is not a BIBO stable system. Why? Because for a certain bounded input, we can produce an unbounded output. Let's give now an example where we are given a transfer function, and we will try to tell whether the system is BIBO stable or not. So take, for example, the transfer function shown here, 1 over s squared plus 1. So take a bounded input, for example, take u of t is equal to 1. The Laplace transform of that is 1 over s, and the output is, of course, input times transfer function, so it is 1 over s squared plus 1. And if you take the inverse Laplace transform, which you can do as an exercise, you will find that x of t is 1 minus cosine of t. This is a bounded output, so for a bounded input we have a bounded output, and someone could say here that the system is BIBO stable. But this is wrong, because if we look at the definition again, the definition says that x is bounded for any possible bounded input, for any u. What we showed here is that the output is bounded for this particular bounded input. And it becomes clear, it starts to become a little clear, that the question of whether a dynamical system is stable is not an easy one. Actually, using the definition, we would have to test again all possible bounded inputs. And that space of bounded inputs is, trust me, it is absolutely vast. It's huge. We wouldn't be able to traverse it in any possible way. So what we need here are some proper mathematical theorems that we can use to tell whether a dynamical system is stable or not. Otherwise, we could end up in situations like the Tacoma Bridge, which wasn't designed properly, and a certain vibration caused from the wind made it just collapse. So here is the first criterion, and this is a very useful theorem, a very useful result. Let me write it down for you. So this is the theorem, a linear dynamical system, it says, with impulse response g. You remember what the impulse response is? G of t. This is the inverse Laplace transform of g. And the definition of the impulse response is that it is the response of the dynamical system when the input is equal to the Dirac pulse. So again, a linear dynamical system with a given impulse response g is BIBO stable. We know what that means. If and only if, oh, that's very good. It means that we will have a necessary and sufficient condition. So it is a strong theorem. So if and only if g, the impulse response, is absolutely integrable. What does it mean for a function g to be absolutely integrable? It means that this integral here, the integral of the absolute value of g, is a finite number. It doesn't matter what, but so long as this is not equal to infinity, then the system is BIBO stable. And this theorem now has a very interesting proof, because it uses a result we might have skipped or forgotten, but it is a very important result. We know that in the S domain, where we have u of s here as an input and x of s as an output, the output x is equal to g of s times u of s. So this is well known here, right? But what is the output x of t? X of t, we know very well that is the inverse Laplace transform of x. But what is x? X is g times u, so this is the inverse Laplace transform of g times u. And what is the inverse Laplace transform of a product of two functions? It is the convolution. It is the convolution of the inverse Laplace transforms. And what is the inverse Laplace transform of g, uppercase? It is g lowercase by definition. And what is the inverse Laplace transform of u uppercase? It is u lowercase. So let's write it down again clearly. X of t is g asterisk u of t, g convolution with u of t. So if we know the impulse response of a dynamical system, we can tell its output for any given input u. And we can use this very simple equation here to prove that if G is absolutely integrable, parenthesis. Again, what does it mean? It means that there is a number, let's call it L uppercase, which is equal to, and this is not equal to infinity. So if G is absolutely integrable, then is BIBO stable. Now this means, BIBO stability means that the output of the system, mainly x of t, will remain bounded, so the absolute value of that signal will remain below some finite value for all t, so long as the input remains bounded. So assume that U is bounded. U of t is below, in absolute value, below some number a for all t. Then this is equal to this convolution. Don't forget the absolute value. Now, how do we proceed? Apparently, we need to use the definition of the convolution. What is the convolution of the two functions g and u? So this is the definition of the convolution. We're trying to show that this is below some upper bound m. So the first thing we can do, is there a space there? Can you see it? Perhaps I need to create some space here. So let's continue up here. The absolute value of an integral is smaller than or equal the integral of the absolute value the absolute value of the product of these two functions is equal to the product of the absolute values. Very simple. Now, this is the integral from 0 to t of absolute value of g of tau. And now we'll use the fact that this function u is upper bounded by a. We use this as we stated it as an assumption that u of t is bounded. So if u of t is bounded, let's see what happens to the output of the system. So let's say this is a, and of course we can move a outside. So this is equal to a times from 0 to t g of tau d tau. Now this is from 0 to t. We could have started the proof using the other definition of the convolution from 0 to infinity. But it doesn't matter, from 0 to t works as well. Don't forget what we're trying to do here. We're trying to show that if u is bounded, then x is bounded. So far we haven't made it, because we haven't shown that this is below some fixed number. But this is an integral from 0 to 3 dots. An integral of a non-negative quantity. So the more t increases, the larger this value becomes. So the largest it can become is if we take t to infinity. So this is the largest this value can become. But look what we have here. We have the integral of the absolute value of g. Rings a bell? That's exactly L. L is equal to that thing, which is not infinity. So this is equal to AL. And look what we have proved here, that the absolute value of x is no larger than a number, and we showed actually that this is true for all non-negative times t. And we have shown, I'm repeating it, that if g is absolutely integrable, then the system is BIBO stable. We could prove the other way. So we proved the first part. It says here, if and only if. We showed that if g is absolutely integrable, then the system is BIBO stable. It remains to show that if the system is BIBO stable, then g is absolutely integrable. That is a very nice proof. It's not difficult either, but you can find this in the textbook. So that's the first theorem, and we can use it actually to check whether a given dynamical system with a given transfer function is BIBO stable. So let's give an example. Take g of s is 1 over s plus 1. What is the impulse response of that system? The impulse response is exponential of minus t. And what is this integral? Let's see, is this absolutely integrable? So take the integral of g from 0 to infinity, the integral of the absolute value of g from 0 to infinity, which is equal. Now look, we don't need the absolute value because this is a positive quantity for all times. So this is e to the minus tau d tau. What is an antiderivative of e to the minus tau? It is minus e to the minus tau from tau 0 to tau goes to infinity. As tau goes to infinity, this whole quantity goes to 0, so 0 minus e to the minus 0, which is minus minus. So this is equal to plus 1, which is good, it's not infinity. And we just proved that G is BIBO stable. Yet another example, a second example. Take g of s is 1 over s minus 1, so g of t. Now this function, you know that this function looks like that. Goes to infinity. So this area, the area also goes to infinity. It's impossible for the integral to be finite unless this goes to 0. If it goes to 0, it doesn't mean it's finite, but it is necessary, it's absolutely necessary that this goes to 0 for the integral to be finite. This goes to infinity. So g is not absolutely integrable. And we conclude that g is unstable in the BIBO sense. Now we can give a few more examples. For example, g of s is 1 over s squared plus 1. So very quickly, what is the inverse Laplace transform of that? The impulse response here is sine of t. Again, sine of t, or better, the absolute value of sine of t. Again, this doesn't go to 0, which is a necessary requirement. So we can say safely that this system is BIBO unstable. I hope you can see it down there. So this system is BIBO unstable. What does it mean that this system is BIBO unstable? It means that we can find a certain bounded input, u, that produces an unbounded output. So this means can find a bounded input that produces an unbounded output. In fact, we tried that previously, and we applied a certain bounded input that produced a bounded output. But there are certain inputs that are bounded and produce unbounded outputs. So here, u of t is sine of t will produce an unbounded output. Why? Because that will be the S domain, the Laplace transform of u, and x of s will be 1 over s squared plus 1 squared. And we know very well that x of t in that case is unbounded. I will leave it to you to find the inverse Laplace transform of x of s and write x of t in the time domain. Now the good thing about this theorem is that it allows to tell whether a system is BIBO stable by looking at the impulse response of the system and telling whether it is integrable, absolutely integrable or not. The disadvantages of the theorem is that first of all we need to have the impulse response, which is not impossible. We know how to do it. We know for every g of s, that is a rational function, we know how to do it, but it might be a little cumbersome. So that's one difficulty of using this theorem. And the second one is that we need to tell whether it is absolutely integrable. Again, it's not too difficult, but we have to determine an integral, which takes some time. So these are the disadvantages, which we will address with some other more powerful theorems and methods. But the advantages are that we don't need to check for any possible bounded input, which would have been impossible actually. So it is a very, very powerful tool, and it is also a necessary and sufficient condition. So if the function g lowercase, if the impulse response is absolutely integrable, the system is BIBO stable. If it is not, then we are certain it is BIBO unstable. So thank you very much for watching, and until next time, goodbye.